In our RL circuit, we have our battery, we have our resistor, we have our inductor, and we'll have a switch. Let's say the inductance is equal to 4.5. 4.5, what are the dimensions for inductance? Winter? Henries. The inductance is equal to 4.5 henries. The resistance is equal to 6.0 ohms, and the EMF is equal to 24 volts. I have a couple of questions. The first one is, what is the electric potential difference across the inductor when the current in the circuit is equal to 1.50 amps? And part B, what is the maximum current in the circuit? We know the inductance, the resistance, the EMF. We're looking for the electric potential difference when the current equals a certain value, and we have our circuit in RL circuit. How would you like to begin? Sierra. Technically negative. Oh, okay. Okay. I agree with that statement. We don't know di dt, right? We know the current at a specific time, but we don't know how that current is changing as a function of time. Okay, Jenkins.
Delta V of a loop equals 0.
Okay. The electric potential difference around a loop equals 0. Walk all the way around the loop for me. Nitish.
Well, you start with a positive EMF. If you're going, clockwise above the loop. Minus the potential difference across the resistor. Minus the potential difference across the inductor.
Okay. So if we're looking for the electric potential difference across the inductor, that's equal to the EMF, or sorry, the electric potential difference across the resistor. No, it is. The EMF minus the electric potential difference across the resistor. The EMF minus the current times resistance. The electric potential difference across the inductor is equal to the EMF, which is 24, minus the current, which is 1.5, multiplied by the resistance, which is 6. The electric potential difference across the inductor.
$15.
15 amps, or 15 volts. So the electric potential difference across the inductor, 15 volts. Okay. Current maximum, how are we going to solve for that? Look. Current maximum, Loki. Tell me when it occurs. At the end, okay. When the current is at a maximum, which is at the end, time t equals infinity, what do we know about the current? I'm sorry, go ahead, Hans. It's not changing. We know that the current is a maximum at t is approximately equal to infinity, where di dt is equal to 0. Okay, from there, stays. Okay, the current as a function of time, where we could go through and derive the equation for the current as a function of time. It's equal to E over R minus, all those 1 minus, et cetera, et cetera. Okay?
T is approximately equal to infinity, so.
True, true. Now, I'm going to stop you for a second. 1 minus e to the negative RT over L. And the reason I'm going to stop you for a second is because This actually is where most people go when we start this problem. Because we took all this time to derive this long equation, and we could go through and derive it again, right? But the thing is, as AP students, you like to make things harder than they actually are. You do. Travis?
At times grounded, the rate of the current is 0, so delta V of the inductor is 0.
Notice at this time, that means the electric potential difference across the inductor is equal to 0. Therefore, coming back to our equation, the electric potential difference across the loop is just going to be, I'll bring it up over here. 0 is equal to, writing out the whole thing, the EMF minus the electric potential difference across the resistor minus the electric potential difference across the inductor. This is equal to 0. We get 0 is equal to the EMF minus current times resistance. Therefore, current times resistance equals the EMF. The current is equal to the EMF divided by the resistance. This is your maximum current. The EMF is equal to 24 volts divided by the resistance, which is 6. 24 divided by 6, or 4.0 amps. Okay, my point is this. There's nothing wrong with deriving this equation. It would be correct, except that this would take a lot of time, and you don't need to do it. And you want to maximize your time. So deriving this equation for this problem would not be a good idea. Parag.
So like if it asks for like the whatever at like a start point or an end point or at like infinity, you can probably do that. But if they ask for like a specific time in between, you pretty much just
So notice with this specific one, they said not at a specific time, but at a specific current, right? Because they specified a current, you could go through and solve it. If they had specified a time, then you would have to go through and do this. Most likely.